Now we'll add the file for LeetCode 21. Merge two sorted lists. Let's open the file so we can build the solution step by step. No imports are needed for this problem. We'll start with a small header to describe what we're building. This file implements the classic merge of two sorted linked lists. First, we define the list node class used by LeetCode. Each node holds a value and a pointer to the next node. List node is the basic building block for our linked lists. Now we'll add a solution class, where LeetCode expects the merge method to live. The solution class will contain our mergeTwoLists method. Here is the method signature. It takes two sorted list heads and returns the merge head. We'll merge by walking both lists in ascending order. We create a dummy node to simplify edge cases and a current pointer to build the merged list. The dummy node lets us avoid special casing the head of the merged list. We iterate while both lists have nodes. Attach the smaller node to current.next. This loop maintains sorted order by always choosing the smaller head. If we took from list 1, advance list 1. Otherwise, connect current to list 2's node. The else branch handles the case where list 2's value is smaller. After attaching from either list, advance current to continue building the result. Keeping current in sync is crucial to append at the tail efficiently. When one list is exhausted, append a remainder of the other list since it is already sorted. This quickly connects any leftover nodes without extra loops. Finally, return the real head, which is just after the dummy placeholder. Returning dummy.next discards the helper node and yields the merged list. Let's add a small test harness. First, a helper to build a linked list from a Python list using a dummy head. This function converts a list of integers into a linked list. Iterate through values, append nodes at the tail, and return the real head after the dummy. Returning head.next skips the dummy node and gives the actual list head. Next, a simple printer that collects node values so we can visualize the merged result. This helper will print the list in a readable arrow-separated format. Advance through the list and print the values joined by arrows for clarity. This output helps confirm the merged order is correct. Finally, let's build two lists, merge them using our solution, and print the result to verify it. We should see 1-1-2-3-4-4, confirming a correct merge. Now we'll add the main Python file, where we'll implement generate parentheses. Let's open the file to begin coding step by step. Let's start by noting the time and space complexity, and then import list for clear type hints. We import list so our method can advertise that it returns a list of strings. Now we'll add the solution class that LeetCode expects. We'll leave space to define our method next. This class wraps our algorithm so LeetCode can instantiate and call it. This method takes in and returns all valid parentheses combinations. We'll put the helper inside for clarity. Our public API, given in pairs, produce every valid string using backtracking. Now let's create the helper. It accumulates characters, and when the string reaches length 2 asterisk n, we record a valid result. This base case stops recursion once we've placed all 2 asterisk n characters and saves the completed string. Here are the choices: add, if we still have some left to place, and add, only if it won't break validity. This guard ensures we never place more, then so partial strings always remain valid. Next, we initialize the results list and start the recursion with an empty string and 0 counts. We'll collect every valid combination in this list as backtracking explores the search space. Finally, we return the accumulated list of valid parentheses strings. At this point, all valid strings have been appended by the helper and are ready to return. Let's try n equals 3. We should see 5 well-known combinations like n, This first test exercises the branching logic enough to verify both and decisions. And with n equals 1, we expect just one combination, a single pair. Feel free to change and to explore how the backtracking scales and still produces only valid strings. Now we'll add the LeetCode 002.3 solution file, where we'll build the code step by step. Opening the solution file so we can start typing the implementation. Let's start by adding a helpful comment and importing list and optional for clear type hints. These type hints make our function signatures easier to understand and maintain. Now we'll add a simple list node class representing nodes in a singly linked list. Each node stores a value and a reference to the next node in the chain. Next, we define the solution class and the mergeKList method that will flatten, sort, and rebuild the merged list. The method receives a list of linked list heads and returns one merged sorted list head. We'll collect all values in an array and use a dummy head with a moving pointer to rebuild the result. Using a dummy head simplifies linking new nodes and returning the final list. Now we'll traverse each input list, appending every node's value to the node's array. This inner loop walks one list at a time, collecting values and advancing through nodes. With all values gathered, we sort them and create a new sorted list by linking nodes in order. Iterating over the sorted values ensures the final list is globally sorted across all K lists. Finally, we return the node after the dummy head, which is the true start of the merged list. Skipping the dummy avoids returning the placeholder node we used for convenient appends. For testing, let's add a helper to build a linked list from a Python list of integers. This builder creates nodes in sequence and returns the head of the constructed list. Next, we'll define a small printer to visualize linked list contents for easy verification. We'll collect values during traversal and later join them into a readable string. We append each value to a list and print them joined by arrows to show order clearly. The output format like 1-, 1-, 2-, 3 makes it easy to confirm sortedness. Now we'll add a small test harness and define the first two input lists. This block runs only when we execute the file directly, perfect for quick tests. We add the third list, call our merge function, and print the merge result to verify correctness. Running this should produce a single sorted list combining all values from the k input lists. Now let's add a new Python file where we'll build the recursive solution step by step. Opening the file so we can start typing our code. Let's start by documenting complexity and importing optional for type hints. We'll use optional to express that our list head can be none. Now we'll define a simple singly linked list node with a value and a pointer to the next node. Each node stores a value and a reference to the next node, which lets us build chains. Next, we'll create a solution class to hold our algorithm, using a recursive approach for clarity. Encapsulating the logic in a class keeps the solution organized and testable. Now we'll add the method signature. It takes the head of a list and returns the new head after pairwise swaps. The return type is optional, list node, because the list might be empty. First, handle the base cases. An empty list or a single node doesn't need swapping. This guard stops recursion and preserves the tail node that has no partner to swap with. Next, identify the first two nodes in the current pair, the head and its next. We name them first node and second node to make the swap steps easier to follow. Now do the recursive stitch. Swap the rest first, attach it to first node, then point second node to first node to complete this pair. We recurse on the sublist starting after the pair, then link that result before flipping the pair. Finally, return second node as the new head for this frame, since we've swapped the pair. Returning second node bubbles the new head up the recursion, rebuilding the list correctly. Let's set up a simple test list with nodes 1, 2, 3 to get started. We build the list by linking each node's next pointer to the following node. Now add the fourth node and invoke swap pairs. We'll print the return head to verify the swap completes. After swapping, the list becomes 2143, and print shows the new head node reference. Now let's create the main Python file, where we'll build the solution step by step. Opening the file so we can start coding. Let's start by noting the problem and the expected time and space complexity for our approach. Our solution will traverse the list once per node on average, so it's linear time and constant extra space. We define a basic singly linked list node with a value and a pointer to the next node. This list node class mirrors what LeetCode provides for linked list problems. Now we'll define the solution class and the reverse kgroup method. We start by pointing a walker at the head. This method receives the head of the list and an integer k, and returns the head after reversing every k-size group. First, we check if there are at least k nodes available. If not, we return head unchanged to avoid partial reversals. This early return ensures we only reverse complete groups of size k. Now we prepare to reverse exactly k nodes by resetting previous and restarting node at the current group head. Previous will trail the reversal as the new head of the reverse segment builds up. We reverse k nodes iteratively, save next, flip the pointer, advance previous, and move node forward. This line performs the actual pointer reversal for the current node. After reversing the current block, we recursively process the remaining list and stitch the segments together. The original head becomes the tail of this block and connects to the result of reversing the rest. Let's build a sample linked list, 1-2-3. We start the list at value 1 and chain the next nodes. We finish the list with 4 and 5, and choose k equals 2 to reverse in pairs. Changing k, here will adjust the group size of the reversal. Finally, we invoke the solution and print the resulting head after reversing nodes in k-sized groups. This executes our algorithm. You can add a helper to traverse and display the full list if desired. Now we'll add the solution file for LeetCode 26 inside the Python folder. Let's open the file and build the solution step by step. Let's start by noting the time and space complexity, then import list for clear type hints. We import list, so our method signature can explicitly say it accepts a list of integers. Now we'll add the solution class, the standard wrapper LeetCode uses for Python submissions. All our logic will live inside this solution class. Next, we define remove duplicates with type hints. We'll use a two-pointer idea. One pointer reads, one writes uniques. This method returns the new length after compressing duplicates in place. Let's initialize the right pointer at 1, since the first element is always unique. Then we scan from I equals 1 to the end. Index marks the next position where we'll place the next discovered unique value. If the current value differs from the previous, we found a new unique value. Copy it to index and advance index. This condition is the heart of the algorithm. It detects boundaries between duplicate runs. Finally, index equals the number of unique elements, and the first index positions hold those values. We return the new length. The array is modified in place up to this index. Let's test with a small example that has a single duplicate run. We expect a new length of 2 and the prefix of nums to be 1, 2. Now try a larger sorted array with several duplicate groups to confirm the logic scales. Here, the expected return length is 5 with unique prefix 0, 1, 2, 3, 4. Let's create a Python folder